Okay, let's use the representation theorem to have some conclusions about when a linear programming problem is unbounded, and if it is not unbounded, and assuming that it is feasible, then how do we make use of the extreme points? I gave you already a theorem without a proof that stated that for a general linear programming problem with any polyhedral, non-empty polyhedral set, if there's an optimal solution, then at least one of the extreme points is optimal, right? And I told you that the proof is straightforward. You should work on it at home. Believe me, it is, if you work out the correct viewpoint on that problem, it shouldn't take more than half a page to give the correct arguments, okay? So what I'm going to discuss right now is a special case of that. We're going to do it or argue for the case with a standard form linear program. So this is for standard form linear programs, okay? So we consider the standard form linear program minimize Cx subject to Ax equals b, x greater than or equal to 0. Now, in the standard form, because of the non-negativity constraints, the feasible set does not contain a line, which means that there's at least one extreme point. For standard form, we have always at least one extreme point, okay? So we may assume x1 through xk be an enumeration of the extreme points. So let x1 through xk be the extreme points of the feasible set where P is defined by these inequalities. And D1 through DL be the extreme directions of P. If there are no extreme directions, then L is 0. Or, well, it's not 0. You just, this second set is void, okay? Null. All right. For any, well, for a picked point x and P, this is a feasible point, we may write x as a convex combination of the extreme points plus a non-negative combination of the extreme directions. So x is going to be equal to lambda I, xi, I going from 1 to k, plus mu j, dj, j going from 1 to L, for some choice of lambda 1 through lambda k and mu 1 through mu L, such that each lambda is a number between 1 and 0. They add up to 1. And each mu is a number greater than or equal to 0. So there's a choice of the lambdas and the mu's with these properties such that x is expressed in this way. So if you call this, say, problem P, maybe LP, P is the polyhedral set, okay? Then we may rewrite LP in the following equivalent form. So this is the let's call it LP prime. We're minimizing C times x, where x is this thing. Subject to a times the same thing since I substituted for x, I don't need the non-negativity here, because what I have here is definitely non-negative, except that I need conditions on the lambdas and the mu's. Lambda I are greater than or equal to 0 and less than or equal to 1 for I 1 to k. Mu j are greater than or equal to 0. And what else? Summation lambda I equals 1. Okay? So here I'm replacing the variables, the components of the x vectors. I'm throwing them away. I'm replacing them with new variables, the lambdas and the mu's. So the variables of this problem, LP prime, are lambdas and mu's. There's no x anymore. What are these xj's? They are known. They are given points. There are too many of them. Nevertheless, you may always pretend that you know them. Okay? Conceptually. Of course, computationally, it's not a good idea. All right, so xj's are, or xi are fixed points or known points. And so xi are known. dj are also known. Lambda i's and mu j's are unknown. So this linear program is in a different space. In other words, your variables are probably more than you want to have. Nevertheless, that's what they are. Okay? Let's clean this up a little bit. This looks too complicated. When you clean this up, so what I'm going to write down is a simplified version of the above problem. We're still minimizing the same objective function. What do we have here? Lambda I is an unknown of the problem. The multiplier for that is c times xi. So there's a c times xi here as a multiplier for that. Cxi is a number. What number is that? Well, the row vector c times the column vector xi. Xi is an extreme point. So the number in the parentheses is just the value of the objective function at the ith extreme point. Okay? C times xi, that's what it is. And of course, you've got the summation, 1 to k. I just multiplied them out. Plus, I multiplied out the second part. So for mu j, my coefficient is c times dj. That's what it is. And then, of course, you've got j going from 1 to L. So, unknown times a known coefficient, unknown times a known coefficient. These known coefficients are extracted from the extreme points as well as from extreme directions, assuming that you already know them conceptually. Subject to, what about this part? Do I need that part? Well, here's the question. What do I know about A times xi? Each satisfies B. AXI equals B, because xi is an extreme point. The dj's, A times dj is how much? 0. Why is it 0? Because that's what you ought to have. To have an extreme direction, you homogenize the initial system, you make the right side 0, A times D will be 0 for any direction of the set, polyhedral set. Okay? All right, so A times xi is 0, A times dj is 0, so everything is 0 here when you multiply, not 0, sorry. This part is 0, so that part disappears. This part is b, so this simply says b equals b, because lambda i's add up to 1. So it doesn't contribute any, well, you don't have to write it down. So there's no need for this, okay? Because, obviously, because we assumed x is a feasible point, and when you express x as a linear combination, well, as a convex combination plus non-negative combination of the other points, the feasibility requirement associated with the equalities is already expressed there. The non-negativity is also dropped out and replaced by these. So this linear program simply has the following constraint. Lambda I add up to 1 with lambda i's being numbers between 0 and 1. Do I really need the less than or equal to 1 constraint here? I don't need that. I don't need that because if lambda I are simply non-negative numbers, if you force them to equal 1, they should be necessarily less than or equal to 1 each. Okay? So we don't need the less than or equal to 1 here. All we need is lambda i's and mu j's are non-negative for I going from 1 to k and j going from 1 to L. So very simple linear program, actually, even though initial statement looks complicated. One constraint here, then non-negativity. That's it. The objective function looks a little bit, well, it requires pre-processing because you have to compute these things. But we don't really deal with this in a computational sense. We deal with it in a conceptual sense, okay? I want to get at the following result from here. So let's give numbers to this. Number 1, number 2, number 3, an, well, number 3. So if you look at number 1, since I'm trying to minimize, if there's a c times dj here, which is negative, what is your minimum cost? Minus infinity. Because if this guy in the parentheses, if the cost is negative for some dj, obviously I can make my mu as large as I want to. The only restriction on mu is non-negativity. So it will be infinity, minus infinity. So LP prime, or 1 implies that the optimal cost is minus infinity if there's a extreme direction dj for which c times dj is less than 0. For the bounded case, this cannot happen because in that case there is no extreme direction in the first place. Okay? But for the unbounded polyhedral feasible set, this is a possibility. Is the reverse, is the converse also true? Yes. If the optimal cost is minus infinity, then there must be at least one dj such that this is true. Actually, we talked about this in the previous lecture. Remember, c times d less than 0. It's the same thing, except that here, all the directions under consideration are extreme directions. Okay? All right. If LP prime or LP, the original LP, so let's just write if LP has a finite optimal cost, then of course it must be the case that C times dj must be non-negative for every j. Because if one of them is negative, you don't have finite optimum. Okay? So, in the latter case, in this case, meaning that, assuming that this is true for every j, we may take mu j equals 0 for every j. In the interest of minimizing the objective function. Why? Because each mu j has a multiplier of either 0 or positive. If 0, mu j can be something else. Still, it will not contribute anything negatively to the minimization. If C dj is positive, obviously you want to make mu j 0, otherwise you won't become optimal. Okay? So, we may take mu j equals 0 for every j. Then, the problem, of course, reduces to minimization of this part drops out, assuming that the optimal cost is finite. In that case, the mu's become 0. And the problem reduces to the minimization of this one. C times xi, lambda I going from 1 to L, subject to summation lambda I equals 1. Sorry, this is k, with lambda i's being non-negative. LP prime for finite optimal situation for the case of finite optimal cost. All right, in this case, what is the minimum you can get here? It's quite obvious. It's not 0. You have to have lambda i's adding up to 1, so it cannot be 0. You cannot pick every lambda to be 0.
It's just the minimum of C xi over I.
Say that again?
The minimum of C xi.
Exactly. You inspect the coefficients of lambda i's. Whichever one is the smallest, that's your best choice. So you set that particular one equal to 1, that lambda equal to 1. The other ones become 0. Okay? So the optimal solution is, in this case, say, C times xp lambda p. Well, actually, lambda p equals cxp, where cxp happens to be the minimum of cxi's I going from 1 to k. Okay? With lambda p taken to be equal to 1 and lambda I taken to be equal to 0 for every I other than p. So this tells you that whenever the optimal cost is finite, there is an extreme point, say xp, which achieves that optimum. There's an extreme point, which is optimal. And of course, extreme points are also basic feasible solutions, so there's always a basic feasible solution which is optimal. That's a strong result. It took quite a while to get there. Nevertheless, we got there. And in fact, we omitted many proofs, but these are foundational stuff. Okay? Once you master these, then the computational stuff is easier for some people. For other people, it may become complicated also. Okay? All right. Extreme points are equivalent to basic feasible solutions. So this particular result has one consequence. You just need to search for the optimum on extreme points or on basic feasible solutions. Search for the optimum on basic feasible solutions. Okay? That, of course, gives you a finite search rather than an infinite search. How many basic feasible solutions can you have? Number of basic feasible solutions is less than or equal to the number of possible basic solutions, because not every basic solution is basic feasible. And that is less than or equal to how much? Let me write it here. Yes, out of n columns of the standard form AX equals B, the standard form A matrix, you are choosing m of them. Because each basis matrix is defined by a choice of m linearly independent columns out of the columns of A matrix. Of course, not every choice could be linearly independent, but that's an upper bound. So it's finite, which is nice. Now, of course, enumerating all, in the absence of any more intelligent method, all you have to do is try out every possible basis, evaluate the objective function at every basic solution, basic feasible solution, throw away the basic ones that are not feasible. And the basic feasible solution that gives you the minimum objective value is your best choice for a minimization. For a maximization, you look for the maximizing one. Okay? The simplex method avoids total enumeration over all basic feasible solutions by doing a more intelligent search. Okay? So, the simplex method works with a subset of basic feasible solutions. How does it do that? Well, it begins at some basic feasible solution, assuming that you know how to begin somewhere. Okay, you begin somewhere, and then you move from that one to a neighboring one, to an adjacent one. And I defined you how basic feasible solutions become adjacent. What was the definition? Two basic feasible solutions in standard form are adjacent if they share, yes, m minus one of the basic variables. Okay. All right. So you move from the current, or the one you started out with, you move to an adjacent one. If there's an adjacent one that qualifies to move to, which means for a minimization it should be smaller in value, or for a maximization it should be larger in value. Okay? So you keep, and then you update the information. You are now at a different basic feasible solution. You again look for the adjacent ones. As long as there's one adjacent which gives you an improvement in the objective function value, you keep doing this. Finally, you get to a point where you're at an extreme point or a basic feasible solution, and none of the neighboring ones are better or give you improvement. You stop there. That's the basic idea. And many of you are already familiar with the mechanism. Okay? So let me give you an example of the simplex method in numerical terms. And then we'll talk about the more general machinery behind it. Well, you can use the simplex method in a number of different ways. One way of doing it is to use the dictionary form, which you probably are not familiar with. Number two way is to use an equation form, which is not very efficient because you have to write down a lot of variables. The third way is the one probably you are familiar with. It's the tabular form, where you just throw away all the variables. You just work with the coefficients of the variables in the constraints. Now, let me do this with the dictionary form first, because it's much easier to envision what's going on with the dictionary form, and then we'll convert it to the tabular form or whatever else we want to work with. So first, you convert this to your standard form. And if you give a name to the value of the objective function, if you call it z, for example, z is defined by x1 plus 3x2. So first I write it down as a constraint. This tells you how z is defined, actually. And then I add slack variables x3 and x4 to put this in standard form, in equalities. So the first constraint becomes x1 plus x2 plus x3 is equal to 6. The next one is minus x1 plus 2x2 plus x4 equals 8. x1, x2, x3, x4, non-negative. Okay? We work with the boxed portion of the equations. These are simply equations. Say that again. Minus x1 plus 2x2 plus x4 is equal to 8. Are you referring to this? I'm just adding a slack variable here, x4, which absorbs the difference between 8 and the left side. Okay? That's it. x3 need not be there. Okay. All right. By the way, z is not required to be non-negative. Z is an additional variable in the problem whose value is dependent on your choice for x1 and x2. Just think of it that way. Okay? All right. So we work with the boxed portion. If necessary, I call this row 0. the new row. The other ones are row 1 and row 2. And if you had m equations, that it would go up to row m. Okay? So my initial basic feasible solution in this case will have the variables x3, x4, and z as basic. So x3 is basic, x4 is basic, these are basic. So the basis matrix is defined by the columns of those. x1 and x2 are non-basic. And remember that for the standard form problem, non-basic means they are set equal to 0. Did I mention that? Okay. Maybe I did not mention that. Let me just revert back to the old stuff. This is sort of a side note. When you had ax equals b, x non-negative, we partitioned this into two parts. A is partitioned as B and N. That's called your basis matrix. That's the non-basic part. Okay? B is M by M, assuming that the rank of A is M. So we're assuming that rank of A equals M. So B is M by M and consists of M linearly independent columns of A for standard form. We talked about this, but I'm just refreshing your memory. Then we partitioned X in the form XB, XN. XB is the M vector, column vector, with basic variables being the components. Xn is the remaining set of variables. Okay? So this is the basic set of variables inside XB. And the variables here are non-basic variables. And what we did was the system AX equals B is written in the form of partitioned form. So it's written as BXB plus NXN. Remember that. And then we set XN equal to 0. In other words, we took those constraints, xj greater than or equal to 0 constraints, as active. That's what we did. Okay? These are the active constraints. So these are the active constraints, and they are definitely 0. Okay? That's what you did. And we refer to them as your non-basic variables. So the only thing that might be missing in the previous information is the term non-basic variables used for these. So non-basic variables are those variables whose non-negativity constraints are taken as equality, which means they are 0. Okay? All right. So with that being 0, of course, this gave you the solution B inverse B, because that disappears. BXB equals B. You pre-multiply both sides by B inverse. You get XB equals B inverse B. And the entire solution is, of course, corresponding to this basis matrix is B inverse B and 0 for the non-basic portion. Okay? So XB and XN. XB is B inverse B, XN is 0. And the objective function value is how much? CB times XB plus CN times XN. So the objective function value is CB times B inverse B. Okay? The other part is 0. All right, so in my example, x1, x2 are non-basic. They are 0. x3, x4, we don't know. We need to solve for them. Okay, let's go ahead and solve for them. So I'm going to use these equations. The first equation is, if you just disregard the non-basic variables, since they are 0, they don't contribute anything to the left side of the equations. So with x1, x2 being 0, z is equal to 0. Okay? With x1, x2 being 0, x3 is equal to 6. And the last one, x4 is equal to how much? 8. In the dictionary form, you actually also write down your other stuff, even though they are 0. This is your current solution, but let's just write them down. So the current value of the objective function plus whatever else you have in the constraint, except that the signs are now the other way. Okay? x3 is equal to 6 minus x1 minus x2. And the other one is x4 is equal to how much? 8 plus x1 minus 2x2. So as long as this part is 0, you've got the current value of the objective function as well as the other variables. That's your solution. x1 is 0, x2 is 0, x3 is 6, x4 is 8. Okay. Here's the next question. I'm going to look for an adjacent basic feasible solution. By the way, is this feasible? This is basic. Is it feasible? The answer is yes, because the current values are all non-negative and z is 0. Okay? Z could be negative, but we don't care about that. All right. So the question here is the following. Can I improve z by exchanging some non-basic variable with a basic variable? Okay, that's what it amounts to, looking for an adjacent one. The answer is yes. If you, for example, declare x1 to be basic in the new solution, it will give you 1 unit of increase. So if you make x1 1, you get 0 plus 1, which is, a rate of increase of 1 unit per unit change in x1, assuming that the other one is still 0, okay? Because we exchange only one variable. Same goes for x2. If you keep x1 0 but increase x2, you get 3 units of increase in the objective function value. The dictionary form, which is this particular form, tells you directly how good or bad a basic variable could be if you decide to make it basic. All right, so from the first equation, the rate of change in the objective function value z is 1 for the first variable, first non-basic variable. And the rate of change relative to the second non-basic variable is 3. Both are good because both increase the objective function value. This is a maximization problem, okay? That's why they are both good. So I can choose either x1 to be basic or x2 to be basic in the next solution. Let's just choose this one because it happens to give a little bit more, okay? At least, that's the temptation most people have. So now, in the new basic feasible solution, I decided to have x2 basic and x2 will become basic. Let's just put it that way. I don't know which basic variable in the current solution will become non-basic. I don't know that yet. So we call that the entering variable. So the entering variable is that one which is currently non-basic, but which will be allowed to become positive in the new solution, which will become basic. Okay. X1 will continue to be non-basic. i.e. 0. Okay? Which variable which is currently basic, so which basic variable must become non-basic? Let's just ask that question and let's try to answer that, okay? And how do you answer that? You just use these equations. Z is equal to 0 plus x1 is still 0, so I disregard that. Well, let me write it down actually. No, let's disregard that. It's better. And x3 is equal to 6 minus x2. x4 is equal to 8 minus 2x2. This is what you've got from your equations here. With x1 still being non-basic. Okay? All right. So obviously I want to increase x2 to the extent possible because z will be increasing by 3 units for each unit increase here. But then you want to also make sure that these stay non-negative in doing so. Okay? So we require these things. Which means, of course, x2 can be at most 6 if you want to keep x3 non-negative. And this one says x2 could be at most 4 if you want to keep x4 non-negative. Of course, the smaller of those will tell you what the blocking or what the limit should be. Okay? So x2 is at most 4. Should it be less than 4 or equal to 4? The answer is yes, make it 4 because then your z will increase up to 12 units. There's no point in making it less. Okay? All right. So when you do that, well, so when you take your x2 to be 4, x4 will become 0. So x4 becomes non-basic in the new basic feasible solution. So we now have do we have a few minutes? How much time do we have?
A few minutes.
Just a few minutes. Okay. So let's just get the new solution, work it out. So we have z equals, well, I revert back to the old equations, but now I'm exchanging the roles of x2 and x4. So what I'm going to do is I'm going to express x2 as a variable on the left side, okay, because it becomes basic. So to do that, first you divide this by 2 and then express it like that. So let me just rewrite the problem in a form similar to star with the new basic, with the new set of basic variables. That's the idea here. So to do that, first we begin with x2, which is the newcomer, okay? x2 is equal to, you just take it to the left. So when you do that, it's going to be 1/2 times 8 plus x1 minus x4. I'm just using the same equations that we have in star, or in the original system here. Okay? So x2 is this much. Substitute this in the other remaining equations in star. So when you substitute the value of x2 in here, you get something for z. What do you get for z? You get z equals 0 plus x1 plus 3 times whatever you've got here, which is 1/2 times 8 is 4 plus 0.5 x1 minus 0.5 x4. Okay? And then you simplify this out, you get something. And you do the same thing for x3, which is 6 minus x1 minus 1/2 times. So it will be 4 plus 0.5 x1 minus 0.5 x4. Okay? We're just using the equation. And the simplification of this tells you that z is equal to, I don't know how much, x1 plus 0.5. So it's 1.5 or 3/2 x1. Well, there's a constant somewhere, 3, so let's write down the constant first. 12 plus 3/2 x1 . No. That's 3/2 from here plus another x1. So it's 5/2. Sorry. 5/2 x1. And then you've got minus 3/2 x4. That's what I have. Okay? So that's z. x2 is equal to, from here of course, 4 plus 1/2 x1 minus 1/2 x4. And then x3 is equal to, from here again, how much is that? 2 minus 3/2 x1 plus 1/2 x4. Let's call this double star. It's essentially the same as your star, except that roles are switched between, the new set of variables. So the next question is to look for a variable to make basic here. In this case, of course, this one looks better. The other one does not look so good. But we're out of time, so I'm going to stop here. Okay?